Okay, so nucleus. And what is it about the nucleus that makes it radioactive?
Unstable.
Why is it unstable?
Oh, because there's an unfavorable ratio of protons and neutrons.
Mm-hmm. Or you have greater than 83 protons. So it doesn't matter what the proton to neutron ratio, if you're past bismuth on the periodic table, all the atoms are going to be radioactive. But anything less than that can be radioactive if its proton to neutron ratio is poor. Remember, we went through that copper isotope check, and sometimes it was good and sometimes it was bad. And so, yeah. A major difference between the alpha and the beta and the gamma.
The gamma just gives off energy, and the alpha and beta produces particles.
So the alpha and beta are particles. So these guys are particles. And this is just energy. So what's the implication of that?
The alpha and beta are more dangerous, right? They can have particles that can get on you.
Yeah, not necessarily more dangerous, just dangerous in a different way. So this can this can be in a contaminant. So you could get alpha or beta on you. You could get something that has alpha or beta emitters, and then you could walk around and pass that off to people. This is not the case with gamma. So if you get hit with gamma, you got hit with gamma. Just like this light is turned on, and the second the light is turned off, there's no more energy being administered to your body. So it's on or off. Isotope?
It's an atom with a different number of neutrons than normal.
Wouldn't say that. So I've got an atom and it's got a set number of neutrons, and then a corresponding isotope would be that same atom with a different set of neutrons. So it's not that it's good or bad, it's just that it's different. So like carbon 12 has 6 protons and 6 neutrons, and carbon 13 has 6 protons and 7 neutrons. Neither one of them is radioactive, they're just different. Changing the ratio will definitely make something eventually radioactive. Like if I go to carbon 14, now all of a sudden the 6 to 8 ratio is bad, so that becomes radioactive. So when we're talking about isotopes, we're literally, every single atom is an isotope to itself. And then we're just comparing it to other atoms of the same element or different atoms. So you could have 2 atoms that have the same number of protons, different number of neutrons, or you could have 2 different atoms that have different numbers of protons but the same mass. Doesn't mean that they're the same. So what does this 20F9 tell you?
That it's fluorine, and it has 9 protons, and that it has 11 neutrons.
So its total mass, total AMUs, atomic mass units, is 20. It has to have 9 protons because it says it's fluorine, and so then the remainder of the AMUs must be total number of neutrons. And then the other ways to express it are 20 with an F or F-20. What type of electromagnetic radiation has a wavelength of 5.5 times 10 to the negative 5th meters? I don't actually think we talked about this in class, did we?
We looked at the chart that has
Mm-hmm.
the wavelength numbers.
Mm-hmm. Oh, that's right. We looked at the chart. So let's pull that thing out. So, Q. nodes, 22, nuclear. So what was it? 10 to the negative fifth?
5.5.
Okay, so 5.5 times 10 to the negative. So we're somewhere possibly down here in the infrared area. Let's look a little more carefully. So if we scroll down a little bit further, there was a zoom in. And so from 400 to 750 nanometers. And what's the number? So this is 5.5 times 10 to the negative 7th. I can make this 550 times 10 to the negative 9th. Are we okay with that mathematically? I'm sorry. It is 10 to the negative 5th. So this becomes 10 to the negative 7th, and that doesn't help me out very much. Okay. So 10 to the negative 5th, I'm looking at this chart here. It looks like my 10 to the negative 5 is smack dab here in the middle of infrared. Okay. What has more energy, the blue or the green light? So if I'm looking at the colors of the rainbow, since this over here is ultraviolet and this over here is infrared, the ultraviolet can actually hurt you. It actually has enough energy to damage you, where infrared does not. So the right side of the rainbow has more energy than the left side of the rainbow. So red has less energy and violet has the most energy. So I've got my green here and my blue here. So that means that the green has less energy than the blue based off of its position in the rainbow. Write the three types for potassium with 22 neutrons. So potassium has 19, it's potassium 19, so K19, and so that's a 41. So then 41K, so then K41. All right, what's missing in this, what's missing? Nice. What's missing in these two equations? What number needs to go right here? 14. And what number needs to go here? 7. And so then that's a nitrogen. So it's 14 plus 0 has to equal 14. And this is everything on this side has to equal everything on the other side. So if there's a 6 here and there's a -1 here, then this here has to be 7 so that those two things equal each other. So what happened here is we had a beta decay of a carbon-14 atom that turned itself into an electron and a neutron, or a nitrogen.
So it was a neutron that lost an electron and it became a proton.
Correct. Yeah. And so I've got this 224 and this 4, so up top this needs to be 228. And I got 86 and this 2, so this down here needs to be 88. So then this is radon. That's what's missing. So that was a radon that had an alpha decay that turned, sorry, a radium that had an alpha decay that turned into a radon. For radiation to give somebody cancer, what needs to happen? So I need a carbon-carbon bond. I need to break a carbon-carbon bond, and that carbon-carbon bond needs to be in the DNA molecule. And then that atom that had its DNA changed needs to proliferate. So to access DNA, what has to be happening?
It has to be at a certain wavelength.
No. most of the time the DNA is wrapped around histones in your cell nucleus, and they're not accessible. So I can't do anything to a cell. The radiation can't do anything to the cell other than kill it if the DNA has been wrapped up. But if it's not wrapped up, if it's being used to make a protein right now, copied to make a protein, or if it's copying itself, if it's undergoing mitosis, then the DNA is exposed and vulnerable. Fundamentally, that neutron is what? Proton plus an electron. So those two things get squished together to make our neutron. So really, I just take an electron and attach it to the exterior of a proton, and now I've got a neutron, since the charges have been canceled out.